Right. Hi, class. Today we're going to go further into organic chemistry. In chapter 14, for the first part, we're going to talk about the functional groups of carboxylic acids and esters. Now, to refresh your memory, I have a slide here with your information sheet, and I'm going to get my pen. Okay. Looking over at the right side where we have the list of functional groups, I'm going to write hydrocarbons here. That was the first organic compounds we talked about. And remember, your hydrocarbons are molecules that just contain carbon and hydrogen. And I took you through 4 groups of those: the alkanes, alkenes, alkynes, and aromatics. So we talked about hydrocarbons, we talked about alcohols, ethers, aldehyde, ketones, and on the very bottom is the thiols, which we talked about in the alcohol chapter. So those are the functional groups we've covered so far. Chapter 10 then is going to take us through carboxylic acids, esters, amides, and amines. So that's what we're going to focus on here today. I also want to refresh your memory on the prefixes. So for organic compounds, when you're naming them, the prefix meth indicates there's 1 carbon. Eth is for 2 carbons, prop is 3 carbons, bute is 4. And when you get more than 4 carbons, then you just come over here to your normal Greek prefixes and continue on. So penta would be 5 carbons. So I think we're all familiar with that. So that's where we're going to pick up today. Now, carboxylic acids contain what we call a hydroxyl group. And hydroxyl groups contain a carbonyl group. So carbonyl group, remember, is the carbon double bond oxygen, and that carbonyl group is attached to the hydroxyl group. Okay, so I had told you guys to memorize those 2 groups in a previous lecture. Now I want you to memorize that when those 2 are bonded together, like I have boxed off here, it's called a carboxyl group. Another thing I want you to notice is the 2 different ways of writing this carboxyl group. Here it's drawn out for you, like it is on your information sheet where we're showing you the carbon double bond oxygen. But a shorthand way of writing a carboxyl group is right here, where you bring that double bond oxygen just down into the long chain. So when you're doing your homework and the questions are asking you for the condensed structural formula, you're going to want to type in the carboxylic acids this way, where you do a carbon, oxygen, oxygen, hydrogen. So be able to recognize both of those as your carboxylic acids. So some names and sources of some carboxylic acids. I'm not going to ask you to name any carboxylic acid, but I do want to make you aware of the ending of carboxylic acids and kind of some of the system to naming it, because you might need to go from the name back to the formula to do some of your homework problems. So the first thing to know is that carboxylic acids are named by ending them oic acid. So they're named as like the methane or ethane. You drop the E and add oic acid. Now you won't ever have to do that because I'm not going to ask you to name. But you do need to kind of identify the ending here as oic acid and say, okay, that's a carboxylic acid. I see the prefix meth, so that means I have a carboxylic acid with 1 carbon. And if you look over here, sure enough, here's my carboxylic acid, because I see the carboxyl group, and there's just 1 carbon. So that would be methanoic acid. Ethanoic acid would have 2 carbons. The more common name for ethanoic acid that we're more familiar with is acetic acid. Remember that this was the 1 weak acid I expected you guys to memorize when we were in the acid-base chapter. So that's acetic acid, which we find in vinegar. 3 carbons would be propanoic acid, 4 would be butanoic acid. They also have common names, propionic acid and butyric acid. And here's a list of some of the places where you might find those acids. So the acidity of carboxylic acids. Carboxylic acids we know are weak acids. They ionize in water to produce what we call a carboxylate ion. I'm not going to expect you to know that word. However, I do want you to remember the hydronium ion. Okay, so acids, when you put them in water, they donate their hydrogen ion, and that hydrogen ion will go to the water to make hydronium. So that's what we're showing here. This is acetic acid. The first thing to know is which hydrogen a carboxylic acid donates. Okay, and it's always going to be the hydrogen that is part of that hydroxyl group. So this is the hydrogen ion that is lost when you put the acid in water. That hydrogen ion then goes and combines with water to make the hydronium. Okay. Remember also, when that carboxylic acid loses the hydrogen ion, it's left with a -1 charge. Okay, so when I grade you on the reactions of putting a carboxylic acid in water, I am going to attribute some points to having that -1 charge, and then the +1 charge on the hydronium. So be watching for that. Another thing I want you to watch for, especially for the homework sake, is that since they're weak acids, you get this arrow going in two different directions, indicating that it reaches a weak equilibrium. The reaction just doesn't go 100% to the right like it does if you have a strong acid. So when you're doing the homework and you're writing equations for carboxylic acids and water, remember to put your arrow going both directions for an equilibrium. So the neutralization of carboxylic acids. So if you remember from the acid-base chapters, acids and bases will neutralize each other. So carboxylic acid salts are the product of the neutralization of a carboxylic acid with a strong base. So if you remember from the acid-base chapter, when you reacted a strong acid with a strong base, you produced a salt and water. So we're going to see a lot of the same thing here. So here's acetic acid written with the COOH instead of showing you that carbonyl group. So this is the H that the acetic acid is going to donate. This is the OH that the base is going to donate, because remember, one of the definitions of a base is it produces hydroxide in water. These two are going to go together to make water. And so that's where we get our water over here. And what's going to be left then is your the anion that's formed when acetic acid loses the hydrogen ion, and then the sodium ion then is going to come balance off the negative charge. So this is what we call the carboxylic acid salt, because we have the charges. Now, in organic chemistry, a lot of organic chemists will write the negative charge and the plus charge inside the salt. And that's totally acceptable. But when you're doing your homework, I noticed that the Mastering Chemistry software doesn't allow you to put that negative and positive sign in. And that's totally acceptable too. So just know that when you're doing your homework. Carboxylic acid salts are used as preservatives and flavor enhancers. Here's an example of that. Monosodium glutamate, which is more commonly known as MSG, is often used as a flavor enhancer. And if we look at that, what's happening is you start with glutamic acid, and here glutamic acid actually has 2 carboxyl groups, but one of them here will react with the base. So the carboxylic acid group will donate its hydrogen ion. The base will donate its hydroxide ion. Those guys will come together to make water. And then the sodium ion will counterbalance this anion from the glutamic acid. And that's what we call MSG. So here's a learning check. Go ahead and write the equations for the reaction of propanoic acid with do water and then do potassium hydroxide. So propanoic acid, we know the prop means it has 3 carbons, and oic acid means it's a carboxylic acid. So if I did this backwards here, I would start with my carboxylic acid. And I know that there is 3 carbons because of the prop prefix. And then I have to put all my hydrogens in there. So my ending carbon would have 3 hydrogens. This carbon is going to have 2 hydrogens. So that's propanoic acid. I'm going to put that with water. And in organic chemistry, we tend to like to write water HOH. And once again, this is a weak acid, so I'm going to remember that it reaches an equilibrium. And this is the hydrogen that is lost. It donates this hydrogen ion, and that hydrogen ion goes to the water. So I'm just going to write my propanoic acid without that hydrogen ion. But I'm going to remember that I have to put a -1 sign by that oxygen, because it lost not just a hydrogen, but the hydrogen plus ion. And then I'm going to have hydronium, and I'm going to remember that hydronium is a +1 charge. Okay, when I put propanoic acid with a strong base, I failed to mention this on the previous slide, but those reactions are going to go 100% to completion because of the strong base. So those reactions just need an arrow going to the right. So let's think through this. My propanoic acid is going to donate its hydrogen ion. The base is going to donate its hydroxide ion. Those two are going to go together to make water. And then the K, potassium is going to come over here and balance out the oxygen's negative charge. So we're going to have CH3, oops, I made a mistake here, CH2. And then this anion, which you can put the negative sign here or you can leave it off. And then that potassium cation will balance out the charge. Remember, in your homework, you do not want to put that positive and negative sign there. And then I'm going to have water as the other product. Fatty acids. They are simply carboxylic acids where the R group portion typically contains more than 7 carbons. So here, if we look at this, here's my carboxyl group. So this just means it's carboxylic acid, but since the R group has a lot more than 7 carbons, we don't call it a carboxylic acid. Usually we call it a fatty acid. Base neutralization of fatty acids produce soaps. So here is a fatty acid. We're reacting it with sodium hydroxide. The fatty acid is just going to do what all good acids do, and they lose their hydrogen ion. The base is going to donate its hydroxide ion. And those two are going to come together to produce water, which is not being shown on this slide. And then the sodium ion then is going to come over here and hang out with the oxygen anion. So this right here is what we call a soap molecule, and we're going to talk more about it. But it's good to know the way you make soap is to react a fatty acid with a strong base. So in a soap molecule, if you can see here, they're telling you that this part right here, the hydrocarbon part, the part that only contains carbon and hydrogen, is a nonpolar tail, and it's going to be hydrophobic, which means that it is fear of water. So it doesn't want to be around water. Over here, they call this part of the soap molecule the polar head. It's polar because it's ionic, meaning it will be attracted to water, and so they call that hydrophilic, meaning water-loving. So here's the cleaning action of soap. A soap contains a nonpolar end that dissolves in the nonpolar fats and oils, and then a polar end that dissolves in water. So the way we often shorten that nonpolar tail is we do this little zigzaggy line to represent the carbons. If I go back to the previous slide, you'll notice all the carbons in that big long chain have 4 bonds to them, so they're tetrahedral shape. So that leads us to this kind of zigzaggy shape around each carbon. That's kind of how we symbolize the non-polar tail of the soap molecule. And then here's the polar head. So what happens is this non-polar tail, if you remember when I talked about likes dissolving likes, so since the tail is nonpolar, it wants to hang out with the oil and grease, which is nonpolar, and then the polar head wants to hang out with the water. So what ends up happening is the soap forms groups of soap molecules, which are called micelles, and I wish I had bolded and underlined that because that is a word I'd want you to know. So micelles then can dissolve in the water, then are washed away. So if you look at the picture, here's the yellow is representing the grease or the oil, and your little squiggly lines are embedding in the grease, and then you have the polar heads on the outside because they don't want to be inside the grease. And what ends up happening is you have these little spherical shapes which now can dissolve in water, where usually oil and water don't mix and they make 2 layers. But when you get these micelles, you can actually get the grease to dissolve into the water, and then it can be washed away. Okay, so that is carboxylic acids. Switching to esters, then, our next functional group. This particular functional group is known for having a lot of nice fragrances. They're used in perfumes. Most of them smell good. A lot of them are in your flowers and fruits, things that have a nice flavor. So in an ester, the hydrogen in the carboxyl group is replaced with an alkyl group. Now remember, the term alkyl group just means it's a hydrocarbon group. So a grouping of carbon and hydrogens. So basically what used to be a carboxyl group, where we had the carbonyl group and then this OH, they're telling you they've taken off the H here, and so this is the part that used to be the carboxyl group, and they've replaced the H with some carbonyl group. It doesn't have to be a methyl group, but they're replacing it with an R. So that's how you're going to identify your esters. It's going to be R, and then your carbonyl, and then your O, and then another R. So make sure you can see that on your information sheet. Esters are going to end with the ending 8. Some ester products. So we made aspirin in lab. So aspirin is used to relieve pain and reduce inflammation. It is an ester of salicylic acid. So that's what we did in lab. We measured out some salicylic acid, and we had used acetic anhydride, which then turned into this acetic acid during the reaction. And so when you mix salicylic acid with acetic acid, you end up making this ester. And if you can locate the ester group, here would be our ester group, because we have a carbon here. So this would be my R, O, carbonyl group, and then another R. So notice this is flipped around from your information sheet. On your information sheet it has R, carbonyl group, OR, and now we're flipping it around the other way. So you need to be able to identify these groups flipped either direction. Oil of wintergreen is used to soothe sore muscles. It is an ester of salicylic acid and methanol. So in this particular case, when our salicylic acid group, the hydroxyl group doesn't react this time, and it is the carboxylic acid group that reacts with the alcohol. So some esters in plants. Esters give flowers and fruits their pleasant fragrances and flavors. So here's just a few for you to look at. It turns out that pears here have got this particular structure. And I'm not going to test you on this. What I want you to be able to do is be able to look at these structures and identify them as esters. So over here we have an R group, and then we have our carbonyl group, an oxygen, and this would be another R group. So this would be an ester. This particular molecule is what gives bananas their flavor, and here is the molecule that gives oranges their flavors. So be able to identify all of those as esters. There is a reaction that I expect you guys to be able to learn and write out, and it's called esterification. And esterification is the reaction of a carboxylic acid with an alcohol. And in order for this to work, it needs to be in the presence of a strong acid catalyst to help this reaction go in the forward direction. So you are going to look right here and tell me what this functional group is. And I hope you tell me that this is a carboxylic acid. And over here, this molecule is an alcohol, because I see my hydroxyl group bonded to an R. So what happens in an esterification reaction is this OH group from my carboxylic acid is going to react with the hydrogen from the alcohol. And these two are going to go together to make water. And then this oxygen right here is going to bond to this carbonyl group. And notice then we are left with an ester. So this particular reaction is called esterification. And you make esters by using a carboxylic acid and an alcohol. So there's a particular general trend we see when we're doing reactions of carboxylic acids, esters, and amides. These tend to be hard reactions for students. So I'm going to try to sum up this general trend. And if you memorize this and you just do this every single time, then you're going to be fine. Now remember, when I'm talking about carboxylic acids, this general trend doesn't work when you're putting the carboxylic acid in water and in a strong base, like we talked about just a couple minutes ago. Okay, we're going to use this trend when you put a carboxylic acid with an alcohol. So what you do, so I recommend putting this on a note card and memorizing these. Your first step is to find the carbonyl containing compound and break off a piece of it that is attached to the carbonyl carbon. So if we were to look at these molecules up here, here's my carboxylic acid. So find the carbonyl containing compound. So if we focused on our first one here, all of these guys contain a carbonyl group. Okay, so find your carbonyl group, break off a piece of it that is attached to the carbonyl carbon. Never break a carbon-carbon or a carbon-hydrogen bond. Okay, so there's some rules you got to remember. So basically we have to break on one side of the carbon, and you have to decide which one. Well, if you go to break it on this side, you're breaking a carbon-carbon bond, which isn't allowed. No carbon-carbon bonds and no carbon-hydrogen bonds. So that means we're going to break it right here. We're going to break between the carbon and the oxygen. You're going to find that you're always either breaking between a carbon and an oxygen or a carbon and a nitrogen in this chapter. So That's step one. Break between the carbonyl carbon and the oxygen. And same thing if it's an ester. Break between the carbonyl carbon and the oxygen. If it happens to be an amine, an amide, which we haven't talked about, you're going to break between the carbon and the nitrogen. Okay, so that's step one. Step two is in the second molecule, which I'm not showing you here because I don't have the reaction, but in the second molecule, it's always going to either contain an OH group or an NH group. And in that case, you're going to break off the piece that is attached to the hydrogen at the OH or the NH bond. So I'll show you that in just a couple seconds. Your last step then is going to switch places of the broken off pieces and rejoin them then to give products. This is an important part right here. Make sure you understand that. Make certain you make new bonds where you broke old bonds. Okay? So let's try that. Write the equation for the reaction of propanoic acid and methanol in the presence of an acid catalyst. So what was step one? Step one was to break between the carbonyl carbon and the oxygen. So what I'm going to do is I am going to put a circle around the group that I'm breaking off. Okay? Step two then is go to your other molecule and break off between the hydrogen and the oxygen. So you're going to break it here, and I'm going to circle this group I'm breaking off. So another way to say that is just break off everything except the hydrogen. But you have to make sure you're breaking between a hydrogen and an oxygen or a hydrogen and a nitrogen. Okay? So, and then we're going to do just a simple double displacement where I'm going to swap places of these two circles. And let's see if I've got the solution here. Okay, so here's the solution on the next slide. So I'm going to trade places here. So you just start kind of from left to right. So you start off by writing your CH3, CH2, and then your carbonyl group. Now at this point we've broken it here. So this carbon is now does not have an octet anymore, so it's looking for something to bond to. So I am going to, instead of writing what's in the circle, I'm going to write what's in this other circle. But here it gets a little bit tricky because this oxygen right here, since I broke the bond here, this is the oxygen that no longer has an octet. So this oxygen is what is going to bond to this carbon. So I have to flip this CH3O, flip it the other direction, so that the oxygen, which I broke its octet, can bond to this carbon, which I broke its octet. Okay, so basically you just kind of work this thing from left to right. When you get to the circle, you're going to come and start writing what's in the other circle and continue on. And then when I get to my second molecule, I'm going to have to write this OH in the place of this circle. But once again, I have to flip this over because this high oxygen is the oxygen that doesn't have its octet met. And so I have to flip it over to where this oxygen then can bond to this hydrogen. Okay, so it's important you remember you're focused on what elements you broke their octet. When you broke the bond, that particular element or atom is now looking to form a new bond. All right, so acid hydrolysis of esters. Okay, so before I go into this, I just want to recap here for a second. Carboxylic acids have 3 reactions you need to memorize. 1, putting them in water. And in that particular case, the carboxylic acid just loses a hydrogen ion, and the water accepts that hydrogen ion and becomes hydronium. Okay? The second reaction is a carboxylic acid with a strong base. And there the carboxylic acid is also going to donate its hydrogen ion. The base is going to donate its hydroxide ion. They will make water and then a salt. Then the third reaction of carboxylic acids is when you react them with alcohols, and that reaction is called esterification. So that's what we just went over. But for those of you making note cards, I wanted you to remember that carboxylic acids have 3 reactions you need to remember. Okay? Esters have 2 reactions, and this is the first one. You can do an acid hydrolysis. So in an acid hydrolysis reaction, an ester reacts with water to produce a carboxylic acid and an alcohol. So it is just the reverse reaction of what we did with esterification. So in esterification you made the ester. In acid hydrolysis you're going to take the ester and break it apart and get your carboxylic acid and your alcohol back. The word hydrolysis, this is worth talking about. Olysis means to break apart, and the hydro means to break apart with water. So we're going to do a lot of hydrolysis reactions, and that just means you use water to break apart a bigger molecule. Just like esterification, we also need an acid catalyst for this reaction to work. So if we're going to do this, We're going to follow that general reaction scheme that I showed you before, and I told you to memorize those 3 steps. So the first thing I recommend doing is writing water as HOH instead of H2O. I'm going to see if I have the solution here. So you start by breaking between your carbonyl group here, and you rope off the rest of that group. And then you go to the other molecule and you break between a hydrogen-oxygen bond, and you circle everything that's not the hydrogen. So it's always going to be the case that you're just going to have one hydrogen uncircled in the second molecule. And then you're going to swap places. So you start by writing H and then your carbonyl group. So that's where I am right here. I'm over on the product side trying to write this. So I put my H bonded to my carbonyl group, and then I have to figure out what to write next, and I just have to look at the circle in the second molecule. Now in this particular case, I don't have to flip over my OH, because I've already got it written to where the unhappy oxygen that I broke its octet is already written on the side that's going to bond with this carbon. So I just write what's in my second circle. Then when I go to my next molecule, I write that hydrogen that I didn't circle right here. And then I go and I have my circle, but I'm going to write what's in the other circle. So I just write the OCH2CH3. And I'm paying attention to the atoms that a bond was broken on, because that's where I'm going to form my new bond. Okay, that was the first reaction of esters, acid hydrolysis. And then the second reaction of esters you need to learn is base hydrolysis. So once again, it's hydrolysis, so we're going to break apart with water. But for a base hydrolysis, we need to have a base instead of an acid catalyst. This one has a special name. Base hydrolysis of esters is called saponification. And the term saponification is it's going to be soap producing or soap making. So base hydrolysis or saponification is a reaction of an ester with a strong base. The products is going to be the salt of a carboxylic acid and an alcohol. Now, this is worth maybe making a note card of. Salts of carboxylic acids, another word for that is soaps. Soaps are salts of carboxylic acids. More technically, they're salts of fatty acids, which are carboxylic acids with 7 or more carbons on them. So here is an example. This is my ester, because I see R, carbonyl group OR, and I'm reacting it with a base, but we don't have to panic. It's just the exact same general trend that we're using. So the first step, find the molecule that contains the carbonyl group. So that would be my first molecule here. Once you have located the molecule with the carbonyl group, you're going to break between the carbon and the oxygen, or carbon and nitrogen. In this case, we have an ester, so it's a carbon-oxygen. So you break that bond. So what we've done is we have now broken the octet of this carbon and broken the octet of this oxygen. So they're now looking for something to bond to. Okay, I am going to circle the group that I'm breaking off the carbonyl group. And then, so that's step 1. Circle what we're going to break off of the carbonyl group. Step 2 is break the oxygen-hydrogen bond or the nitrogen-hydrogen bond in the next molecule. The way I would rephrase step 2 is circle everything except the hydrogen. So I am going to circle this group. And then we're going to trade places of our circles. We're going to do kind of a double displacement. So I'm going to start by writing my CH3 carbonyl group right here. And then I'm about to get to what used to be the circle, so I'm going to replace this circle with the other circle is, but I have to ask myself, do I have to flip it over? Well, in this particular case, I can't just write it NaO, because if I had written it NaO, which is how it's written here, we'd have a problem, because it is this oxygen that was looking for a new bond to form, not the nitrogen. Another thing that can help you, catch yourself if you're making this common mistake is you're never going to have the metal in the middle of the organic molecule. The metal will always be either at the very beginning or at the very end. It'll never be found in the middle. So you have to flip around the NaO so that the oxygen is bonded to that carbonyl group. Once again, you can show this plus sign and this minus sign if you want, but when you're doing your homework online, it won't accept that. Okay, so that's the first step. I wrote down the second circle where the first circle was. Now I am going to start off by writing my hydrogen and then write what was in the first circle. So there's my O, CH2, CH3. And it doesn't matter when you're writing these which direction you wrote them in. Okay, I could have written this second one as CH3, CH2, OH. So you can flip these molecules all around if you want. So here's exactly what I was saying. You just break between the carbonyl group, break between the oxygen and the hydrogen group, and flip these parts around. This is how you're going to want to type it in when you're doing your homework. You just put the oxygen right next to the metal. But it's totally allowed to put a negative and positive sign in there when you're writing your stuff out. So here's a learning check. Write the organic products when methyl acetate, so ending 8 indicates that we have an ester, reacts with the following. So the first reaction is water and an acid catalyst. So I would pause the video and come back and see if you did this right. So step 1, I'm always going to have 2 reactants. I'm going to look for which reactant contains that carbonyl group, and that would be this first molecule. So I'm going to break between the carbonyl carbon and either an oxygen or a nitrogen. Up till this point I've been breaking on the right, but see, I can do this. I can write these molecules either way. Do I want to break on the right? I hope you said no, because we cannot break between a carbon-carbon or a carbon-hydrogen bond. So we have to break it on this side. Okay, so we're going to break there, circle off this group. This is the group that's going to break off the carbonyl group. On the second molecule, we're going to circle everything except the hydrogen. And then we're going to trade places between these circles. So if it were me, I would start off by, okay, I'm at the circle. I kind of work these things from left to right. So I'm going to start off here, but I'm starting off at a circle. So instead of writing this first one, I'm going to write the other circle. But I have to think, do I have to flip it around? And I do have to flip it around because I've got to get this oxygen, since that's the oxygen I broke the octet of when I broke this bond. I have to get this oxygen next to the carbonyl carbon. You may have just written this whole molecule written the other direction, which is totally fine. You might have started off with this CH3 carbonyl group OH, which is totally acceptable. And then I go to my second molecule, working from left to right. I would start off with this hydrogen. Then I reached a circle, so I need to grab the other circle. I have to flip it over so that oxygen is next to the hydrogen. Okay, same trend with the base. I'm going to break between the carbonyl carbon and the oxygen. I'm going to come to my second molecule, circle everything that's not the H, and I'm going to switch places between these. I'm going to go ahead and write this one written the other way so you can see it. In this particular case, I'm going to start here from right to left on this molecule. It doesn't matter. So I have my CH3, my carbonyl group, and now I'm to the part where I hit the circle. So I'm going to write what is in the other circle. Am I going to write this as KO or OK? And I hope you said OK, because I cannot have potassium, which is a metal, in the middle. And this oxygen is the element that was looking for a new bond, and this carbon here was looking for a new bond. And then I go to my second molecule, and I've got my circle first, so I'll just go ahead and write this other circle first. And that is going to bond to this hydrogen that I did not have circled.